Name of this talk is The Best Parts of C++. First of all, I must say about my talks, move to the front, you're doing a pretty good job. I pace a lot also, in case you didn't know that. Please interrupt me if you have questions. That's how I like to do these kinds of things. And this is a great room because I can see everyone who is here. And just for the record, I do training, and this is approximately what my training looks like. I'm going to cover about 25 different major C++ features today, discuss the advantages of each feature, and mention who was involved in the design of the feature. The information that I have for who was involved in the design is based on what I can find from the papers that were used for the actual feature. It's not a conclusive list of everyone who's involved. It's the information that I have available. Some people do get repeated many times on this list because they edit proposals or help with wording, just so you know. Talk is partially inspired by Walter Brown's lightning talk from CVBCon 2018. Thank you. I'm so sorry it took me for so long to say it. Excuse me. Thanking all of his mentors, teachers, and colleagues over the years. And that's a really great lightning talk. And if you haven't seen Sean Parent's keynote from Pacific++ 2018 on generic programming, it's about generic programming, but it's also more about collaboration during the design of the STL and the people involved in that. So let's start with this. What standard do you use? Who uses C++ 98? Who's stuck in C++ 98? Okay. Can anyone say I actually use C++ 03, not C++ 98? Or know the difference between the two of them? Very few people. C++ 11? Okay, that's pretty good. 14? Even better. 17? Are some of you raising your hands multiple times? Multiple projects? Who here is actually using C++ 20 or trying to use pre-release features? Yeah. Right. Excellent. So the first thing that we have is a standard. We have an internationally agreed to document that specifies the behavior of our compilers in our programs. Value of this, really, it can't be underestimated. We have competing implementations that sort out the exact behavior of our programs. Few other languages have this. The first official C++ standard is C++ 98. Uncountably many people are involved in this. Unknowably many, I don't even know who was involved. Actually, I think some of the people in this room may have actually seen this example before, because I bought an interesting magazine at a recent conference that has some really terrible C++ examples in it. Let's just look at this example and ask, is it possible for pi to change? Is it? In this program it is, yes. Is it logical for pi to be able to change? No. If only there was some way to specify that the value of pi cannot change. Const. Well, we're starting and moving in a certain direction here. Const tells the compiler that this value cannot change. If we apply const consistently, we also get to simplify the rest of our variable declarations. If we go back to this version, I really don't like line 7. I really don't. We have this uninitialized area, then on line 8, we're initializing it. If we apply const, it forces us to initialize it. So we have const. Number 2. Most important tools to clean code. An object declared const or access via const reference or a const pointer or pointer to const cannot be modified. Compiler enforces this for us. C++ 98, as far as I can tell, the credit does go to Bjarne Stroustrup, the original creator of C++, for const on this. As far as I can tell, it did not come from any previous language. And yes, You can use east const or west const. They are both valid. Who knows what I'm talking about? Who thinks we spend too much time on this? All right. We started with a double. Now I want a collection of doubles. Does that look all right? Yeah. Yeah. I can use this to sum up the data from this collection. This looks good, right? Maybe? Yeah. We have this uncaught leak here. That's not good. Better? What's that? A bit better. We're not leaking now. So that's something. But only there was some way to automatically delete things when they're no longer needed. Any ideas? What's that? Smart pointers. We'll get to smart pointers. RAII. We've got destructors. Sorry. We have destructors. We can use destructors in our C++ code. We have a cleaner way of doing this. This code technically has no leak in it. Practically has no leak in it. It does have a problem. If you see the problem, you can feel proud of yourself, and we'll come back to it. There is a problem. So number 3, deterministic object lifetime and destruction. We have the ability to use constructor and destructor pairs. RAII combined with scoped values gives us this determinism, removes the need for things like finally, garbage collection. We know when these objects are going to be created and destroyed. I believe also the credit goes to Bjarne Strustrup on this, C++ 98. It's old. Like, this has been as long as C++ has existed. We've got this handy holder for doubles. I'm going to make one for ints now. Maybe something for floats. Only there was some way to avoid repeating ourselves with all this nonsense. Templates. Of course, templates. We can declare this class template. It can hold anything we want. We can declare function templates that can take these values, sum these things up. We've got deterministic object lifetime, and we avoid repeating ourselves with this code. Ultimate in the dry, do not repeat yourself principle. You can write a template that has types and values filled in at compile time. Template types generated by the compiler at compile time. There's no type erasure. There's no Java generic kind of thing going on here. Highly efficient runtime code possible, as good as or better than handwriting in some cases. Template system is Turing complete, though. That's maybe not necessarily a good thing. It's a side effect of the system, but it is interesting at the very least. C++ 98, as far as I can tell, this came from Ada Generics. It was the influence for C++'s templates. Does this code bother anyone? Line 5, copy constructor. Yeah. This code right here, this is what we're coming back to. This only accidentally works because of the copy elision that compilers have basically always implemented. This code would work, but it is technically a copy before C++ 11, a move after C++ 11. Yeah. But we haven't dealt with our move or copy constructors at all on our data thing here. So it's a bit of a pain to get that right. If only there was some way to contain a set of values, maybe something that's already taken care of these lifetime issues for us. Vector? Vector, of course. We can create a vector of data. We can push back all these values in it. What about this sum code? If only we had some utility to add up the range of values here. Algorithms. We can use numeric because, of course, accumulates in the numeric header, not in the algorithm header. I still don't understand that one. So with accumulate, we can add these up. Algorithms and the standard template library. Set, vector, for each, any of, etc., excuse me. Generic set of composable tools, C++ 98, Alexander Stepanov, Mengli, etc. This is where you really should watch Sean Parent's keynote from Pacific++ 2018. He does a great job of covering the history of this. So this is where we are. We have this get data function. We're creating a vector of these values. Everything's templated, and we can sum up the values. Safer, more generic, no potential memory issues. We're still in C++ 98 land. We're moving ourselves forward. We know the amount of data at compile time, right? We know we're pushing 3 things into this vector. If only there was some fixed size container available. Standard array. No dynamic allocation, win-win scenario with knowing the size of the data structure at compile time. At compile time, we know how many elements are in the data structure. One of my one of the guys who comes to my meetup and helps me run it, Lenny Majorani here, refers to this as the negative cost abstraction in C++. In C++, we like to have zero cost abstractions. Array is often a negative cost abstraction because it gives the compiler that much more information at compile time about the work that we're doing. Which, by the way, I know Adi mentioned the user group. Who comes to the local user group? Who will come to the local user group after this conference? There should be more hands up, just so you know. Did you take names? There's cameras. Okay, very good. So we've got standard array. Fixed size, stack-based container. Having the size part of the type gives the more information for optimization opportunities. I believe this came from Boost Array, and Nikolai Yosidis was the implementer of it, I believe. I just looked to the one German that I know in the room to see how closely I pronounced his name. I think I got it close-ish. All right, we've got this thing that takes 3 parameters. I'd really like a version that takes 2 parameters. Maybe a version that takes 1 parameter? Yeah? What? Variadic templates? Is no one gonna? Did you see this? This is what happens when we copy and paste code everywhere. So yes, variadic templates. If only we had some way to initialize all these. Oh, actually, no, we're not to variadic templates yet. Sorry. We will get there in just a moment. Don't tell anyone. All right. There's some way to initialize all these array values in one step. That's what I'm looking for right now. Initializer list. List initialization. So we can just reduce that to this. And we can take it one step further like this and list initialize it in the return statement. List initialization comes in, all right. C++ initialization comes in a lot of different forms. Like a lot of different forms, right? What is there, like 73 different types of initialization in C++? I'm pretty sure it's actually, I think, 17 different types of initialization. It's a lot. But no one can deny that list initialization has changed the way that we've used containers like this. This is much better than having to do push back 4 times. C++ 11, This is where things start to get complicated. C++11 era, there's lots of people named on the papers. But we're looking at Jason Merrill, David van de Voorde, Steven Mzensk. I'm sorry, I can't pronounce Polish last names very well. Gabriel dos Reis and Bjarne Strustrup. That's, yes, a lot of people involved here. Any questions? Okay. I've got parameter versions that take 1, 2, and 3 parameters, and now I want to add versions that take 4, 5, 6 parameters, right? So what did we just say earlier? Variadic templates. Drastic simplification of code needing to match a variable number of parameters, absolutely critical for maintaining implementations of things like standard function. Has anyone, yeah, do you have a question? So the comment was, if you want them all to be the same type, variadic template basically doesn't get you there, which is true. So we have kind of pushed a compile time error. At this version, if we were to pass 5 different types to this, we would get a compile time error at the function call place, because we would try to match this template with multiple types, and it's required to be the same type. So we would get the compile error there. With this version, we would get the compile error at the deducing, where does it move to? Oh, that code has a bug in it. Oops. Yeah. Well, I could change the first parameter of the array to be the std common type t of the variadic parameters pack, and we would get there as well. Yeah. But yes, it does change the nature of the code a little bit. We allow any different number of types to be passed in here instead of requiring them all to be the same type. Although, on the topic of this kind of code, has anyone ever looked at the implementation of boost function pre-C++11? Like completely unmaintainable. What's? 15 or 20 different copy-paste of functions, and that's only because they didn't want, what, the compile time overhead of using boost pp, basically. I've written code like that before in my scripting engine. In ChaiScript, I've got boost pp. I used to have it. I used to have code like this that is now like 3 lines of code because of variadic templates. Douglas Greger, Jaco Jarvi, Jens Maurer, Jason Merrill, Eric Niebler come up on these features. All right, going back to this one, I know you all wanted to say it. Const for all the things. We can use const for here, const for double pi. We know this thing's known at compile time. We can even generate it at compile time if we wanted to. Make a const for function that calculates pi. I actually proved that I could do this, although the compilers did not like it. It takes too long to run. I mean, you know, using something, what? Yes, it didn't like to compile. The compilers did not like to, at compile time, calculate pi because it took too many compile time iterations. But I just proved that it was possible. I mean, just trying to get it to double precision specifically. All right. Const expr. Compile time generation of code and data. C++11. C++11 was very restricted. It was relaxed a lot in C++14. Gabby comes up again, Bjarne Strustrup, Jens Maurer, Richard Smith. Richard Smith is involved in a lot of things. He's also the editor of the standard. We see his name a lot. And Nikolai, again. What should the type of pi be? Who says float? Double? So Well, I was getting there to the it depends question. So okay, let's go this way. Who says I don't care what type is, or what type pi is? And who says it depends on your application? Okay. I generally fall into the other categories of don't care or it depends. So if only there was some way to indicate that we don't care what the type of pi is. Auto. We can use auto here. Const X for auto pi, let it do the right thing. Automatic deduction of variables, a value type, C++ 11, Jako, Yarvi, Bjarne Strustra, Gabby again. I love this quote because I know at least a few years ago when C++ 11 was first starting to get adopted, a lot of people did not trust auto. So I like this quote from Bjarne's FAQ. It says, auto feature has the distinction to be the earliest to be suggested and implemented. I had it working in my CFront implementation in early 1984, but was forced to take it out due to compatibility problems with C. Who has been around long enough to have actually used the C version of auto? Just for the record, I have not, personally. I will demonstrate. This is valid to C++ 98. It means the lifetime of this integer I shall be automatically managed. I can put auto int I in C++ 98. In C99, auto I equals 5. This does not mean automatically deduce the type of I. It means I is by default an integer, because all types in C, pre-C99, were integers. And auto, again, means automatic storage duration, particularly for those of you who were in my class yesterday. This is a way of explicitly saying automatic storage duration. Oh, yeah. Did you like the main signature, by the way? Everything was default int in pre-C99. Is there any way to adjust this previous code to say I really don't care what types I'm using? Template variable? No. Yeah, it wasn't. Yeah, that's true. I'm not going to go there, though. I can use auto return types right here, or something more clever still. Anyone going to comment on what the value of pi is in my code? Okay. It is 3, yes. I see hands going up, like with fingers. It's this many, yes. It is 3. But to be fair, that was also true back here, because we're doing integer division, 22 divided by 7. All right. That's integer division. We'll come back to that. Auto return type deduction for normal functions. This was added in C++ 14. We can do things like this. We can return unnameable types from our functions in C++ 14. This might look silly, but using this for creating higher order functions, functions that take functions and return new functions, this is absolutely indispensable. We can do amazing things like this. Jason Merrill comes up on the paper that I found for this one. So I would like to print a set of key value pairs from a map. I am using C++ 03. We know that auto could help here, but we can't use auto. But what can we use? What tool did we already mention here that Sean Parent would tell us to use? Algorithms. No raw loops. Let's use an algorithm. Okay, I'm in C++ 98. I have a map. I want to iterate over all of the elements. For each, it exists in C++ 98. What do I put there? I want a function, but I have a problem, because with my function, I need the key description and the value description that I want printed with each of these. But I need a callable thing that is, well, it's got an operator paren, basically. A functor, function object, yeah, whatever you want to call it. A way to capture this key description and value description. So I could do this in C++ 98. declare my map value printer that in its constructor takes the key and value, captures them, has the operator paren call operator overloaded, and uses cout to print these things. And then I have my captured values, and now I can use my for each loop nice and cleanly. Right? If only there was some way to create a callable thing. I already hear you all saying it. You want me to use a lambda. All right. We can use a lambda here. Lambda, I'm doing a capture by reference. I take the value type, and yeah, this type name value type, that's really nice. C++11. Lambdas allow us to create unnamed function objects that may or may not have captures. We are not allowed to know the name of the type of a lambda. That's where auto return type deduction helps us a lot too. C++11, many people involved in these lambdas. This line is a bit wordy. If only there was some way to automatically deduce the types of lambda parameters. Auto, generic lambdas. I like to refer to C++14 as a bug fix to C++11 because of things like this. Generic and variadic lambdas. Added in C++14. This one has like 4 standards papers associated with it. Herb, Dave Abrahams, Faisal Vali, with thanks to many names that we've already seen before. Jens Maurer, Douglas Greger, Richard Smith, Christoph Meerwald, John Spicer, Jason Merrill. Lots of people involved in these things. I'm going to go back to the pre-algorithm for a moment and simplify out the template. So I've got this code right here. And I want to point out, part of the reason that I put this talk together is I repeatedly hear from people that C++ has gotten too big and too complicated. Okay? Let's look at this code right here. This construct of iterating over the elements of a container in C++98 was actually the hardest thing for me to learn when I was first programming in C++. I don't know how many times I'm like, what is the spell that I have to cast to get an iterator and iterate over the things in this element, and then it's in this container, that is. If we apply auto, we get here. We've already saved one huge thing. But if only there was some simple way to iterate over all the values in a container. Range-based for loops. This is huge. This is huge in our ability to learn and teach C++, in my opinion. Range-based for loops, item number 14. We iterate over all the elements in a container, works with anything that has begin and end members and functions or C-style arrays. C++11, Douglas Greger, Beeman Dawes are the names that come up on this one. If only there was some way to make this whole data.first and data.second nonsense more readable in our range-based for loop here. Structured bindings. So I can do this. Structured binding C++17, and I can say I want to name this key and value pair here. Used to decompose a structure into a set of identifiers, you must use auto. Just for the record, you cannot specify the type. And the number of elements must match, so there's no way to do a placeholder or skip anything. C++17, Jens Maurer, Herb Sutter, Bjarne Strustrup, Gabriel Dos Reis. Goodness gracious. Template syntax is bulky. Template syntax is bulky. Let's go back to that. Is there something we can do better? Make that simpler? No? Anyone? Oops, I skipped ahead. Yes. C++ 20's concepts. It can actually be auto. We can use the auto concept in C++ 20. So this is now what a regular function can look like. Presuming that the next standard is named C++ 20, but it probably will be. Bryce says it will definitely be named C++ 20. That's on the record now, Bryce. Okay. So I can use this. Who likes that as opposed to the template syntax? Yeah? What's that? First time you see it, so you have to think about it. I'll wait. Yes.
But when I see the function parameter, I don't know is the reader of the code.
Right. So the comment was, you don't know as the reader of the code what are the requirements for this object passed in. And when we had the template, we had that problem still. So that didn't change. But fortunately with concepts, we do have the ability to constrain the types. And we'll get into that in just a moment. Yes?
I think that if you had more than one operating function, you use the dependency of the type. Because before, if you use templates, they're both will be the same type.
Right.
It's going to be a big change.
So if you have more than one auto parameter and you wanted them to be the same type, when we kind of have that problem with generic lambdas, periodic templates again, constraining them to be the same type becomes a little more difficult, but concepts do give us some opportunities for that as well. And you could use static assert, that's true. So you could push the compile time error to a different place. Yeah. C++ 11, two different functions. We want them, one to take a floating point type, one to take an integral type. Who has had to write code like this? Yeah, who likes writing spin-aid code? Wait, there's someone with his hand up back there. Could you, clarify? Job security. Okay, that's the answer I'm getting. Okay. So spin-A allows us to be secure in our jobs. I've never liked this code. I honestly feel like every time that I go to write code like this, wait, where do I need to put the enable if? Is it here? Is it there? Should I make it a function parameter? Should I make it a template parameter? I don't know. Yeah, I'm getting nods. A lot of people agree with that. By the time we get to C++ 17, we can simplify this a bit with concepts. Now, we are, at the moment, relying on someone else having created a floating point and an integral concept for us. We can do this, or something similar to it, in C++ 20. You do need the concept and the auto. As far as I know, this is what has been accepted so far, but it's one of these things that's a little bit in flux. Yes? Does that look right? Okay. I'm getting nods that this looks rightish. Again, I have to thank my local users group because I got the chance to preview this talk with them, and they corrected me on this slide. So this is the world we're leading towards. Concept definitions themselves can be quite simple. We can say, this concept requires that the type is integral. Pretty readable, I think. Allow us to specify the requirements for a type, implicitly create a template that constrains how a function can be used, C++ 20. Andrew Sutton, Casey Carter, Eric Niebler, many, many, many others. There's a very long history to C++ concepts. This code has a potential inefficiency hiding. I am requiring a construction of a string object whenever I call my print map function. Some way to observe string-like things without actually constructing a string? The answer is already given. String view. So I can say this is a string view. It's a string-like thing. Just do what I need to do with it. Non-owning view of a string-like structure. No copies made of the data. We are pointing into it. Added in C++ 17. The names I see come up again: Andrew Sutton, Casey Carter, Eric Niebler. I see a lot of the same names. Cout is quite verbose, relatively slow, and difficult to reason about. If only there was some way of formatting our output a little bit easier. What's that? FMT? It's not part of the standard, you say. Yet, perhaps. It is likely, good chance that we will get something like this. I'm getting hand waves. There is a chance we will get something like this for C++ 20. This has passed initial review. Who would rather do this than the cout? Okay. Subset of the excellent format library has been passed initial approval, being worked on hopefully for C++ 20, allowing for formatting of strings with positional, named, Python, printf style formatting options. Hopefully C++ 20. Victor Zaverbich, are you hoping for C++ 20 also? Yeah, all right. Okay. This is one of his examples from it. So I'm going to scroll back up real quick. The full format lib does have its own print functions as well. He's not expecting to get that, just the ability to format a string, which is why I'm using cout right here with it, but we at least get more readable code. If we bring together algorithms, text formatting, concepts, etc., our map printing routine might look something like this in C++ 20. This is the route that I've started to go, writing my own code here. So I've got my print key value function, and I'm passing that. That's a lambda. I'm defining it locally, and I am printing that here with my algorithm. Only some way we didn't have to do this whole begin map, end map thing when we are working with algorithms.
Could you write the lambda in the for each step?
Could I write the lambda in the for each itself? Yes, absolutely I could. But I've actually personally started leaning towards code like this more often than not. This is no more or less efficient than putting the lambda inside the ranged for loop, inside the for each algorithm. But it gives me more readable code, right? I can read this statement and say, for each of the elements in the container, print the key value.
So why using the lambda? Why not the function?
The comment was, why use a lambda, not a function? And it's true, I could, well, no, actually, I can't use a function here. I carefully crafted this example so that I could not, because of the captures that I am doing on the key description and value description. It was all quite intentional, I assure you. So, have to find a name. Well, yes, okay, so you have to find a good name for your lambda. Naming is hard, right? It is like the hardest thing in computer science. What is it? There's
Naming, cache validation, and off by 1 error.
Yeah, those are the two hardest things in programming. Naming, cache invalidation, and off by 1 errors. Right. Thank you. I would have not remembered that while I was standing here. Yeah, it's true. Naming is hard, but if we do write code like this, it forces us to write maintainable, readable code. But yes, is there some way for us to get around this begin map and end map nonsense? Ranges. This part I'm a little lost on, personally, because in my efforts to test this, I could not get line 11 to compile, and I think that I'm supposed to be able to get something like line 11 to compile. I'm getting no's. Okay. But with ranges, but there is a piping feature of ranges where you can, oh, not yet. Well, it's in all of the examples. In ranges v3, what are we getting in C++20? A subset of ranges v3. Okay, so this you will be able to do in C++20. For each of the values in the map, print the key value. This is the example from cppreference.com, which I assumed was what had been accepted into C++20 from what I understood, but clearly that's a little bit off. But perhaps soonish we will be able to do something like this and actually filter these things with pipes. Eric Niebler, Casey Carter come up on these papers. Eric, I think, has done a considerable portion of the work on this one. This version of my data corrector is correct. This one actually compiles. Well, it is a correct option here. So let's go back to this one. If we apply auto return types, we get this, right? So there's that version where I'm specifying the return type, and there's that version where I'm using auto return types. I didn't really gain very much here. Only there is some way to automatically deduce the type of the array being returned from this function. CTAD. Okay. CTAD. It's 4 letters. What is that? Class template argument deduction. Since I'm gathering that at least a few people have used that, does anyone have a problem with CTAD? No one in this room does? Good, okay, you're all my friends. All right. We can automatically deduce the size and the type of these parameters. Now, we've just moved our compile error again, unfortunately, because if all of the types don't match, then we're going to get a compile error again. But we could use ranges, or concepts or static assert to require that these things all have the same type. Class template argument deduction. C++17, this code is now possible. We can do this vector of 1, 2, 3. That's going to be a vector of ints, and it will contain 3 elements when it's initialized. C++17, Mike Spertus, Faisal Vali, Richard Smith come up on this one again. Now we can simplify our template arguments to this version, but it might make using it harder because of these compile time errors of the types mismatching, potentially. With C++20's auto concept, we could actually write this. Generic, variadic, regular free functions with concepts in C++20. Class template argument deduction. And just for the record, we have lost nothing efficiency-wise here. Whatever we pass into this thing, it's going to directly initialize the standard array with those elements. There's going to be no copies of the array itself. But this, the objects are being copied into the array from the parameters. If in this particular code, if one of the types is an int and one of the types is a float, we would get a compile time error saying that it could not find a matching deduction guide for the array because it would require all the types to be the same. No, it would not. This code would not use implicit conversions. It would be a compile time error on line 3 specifically. Yes? Could a concept be used? Concepts being used, just the fact that I have auto as a regular function parameter. It is the auto concept. So if only there was some way to forward these arguments and avoid copies of the parameters coming into this function. That one's kind of a gimme, right? Standard forward. Now, at this point, I have to admit, this does not necessarily make C++ easier to teach. However, this gives us the tools that we need to write highly efficient functions. At some point, we do unfortunately have to pay the price a little bit. R-value references can be difficult to teach. I know that they can be difficult to teach. Undeniably fix a few holes in the language by allowing us to more accurately reason about the lifetime of objects. C++11, Howard Hinnett, Douglas Greger, David Abrahams, Bernard Schustrup, Lawrence Crowell all come up on this. Guaranteed copy elision. Compilers have always done copy elision on return values, always in quotes. There's in simple code like this where you're returning an object, I've never met a compiler that doesn't use copy elision. It always creates the object at the call site. Yeah. Yes? No, my example is a forwarding reference here. Correct. It is not an R-value reference. But yes, I kind of rolled up the idea into R-value references, saying just that ability being added to the language of R-value references, forwarding references, can deduce R-value references, it all works together. That's what I was aiming. Is that okay? Okay. Yes, that's correct. That is not an R-value reference, that is a forwarding reference. This code in C++17, I can say I have deleted the copy constructor and the move constructor, and the compiler is required to accept this code. Guaranteed copy elision for this code in C++17, neither copy or move. I can teach don't name return values and always get the optimal code. C++17, the only credit I saw for this one is Richard Smith. I did say, no leak, but I'll come back to this code. How is it broken in C++98 again? Copy constructor, copy constructor. Copy elision was happening accidentally. That's a copy, and that means we're going to get a double free. In C++11, it's a move. Now I'm using a move instead of a copy. Actually, this implicitly becomes a move. But what am I getting? What's that? Yeah, the pointer doesn't move, so I'm still getting a double free. Default move constructor will copy the pointer. So if only there was some way to disable problematic operations in our code. Kind of already hinted towards it. Delete. Not very useful at the moment with this code, but we know that it is safe. And non-copyable, non-movable types actually do have a use. Defaulted and deleted functions. Any special member function can be explicitly defaulted. Any regular function can be deleted. This can make our APIs hard to use wrong. I just realized I don't have a great example on this, but I don't want to skip over it too much. I've actually taught this stuff several times recently. And if you've got a function that like everyone keeps passing like a string to it or a const char star, but you're like, no, I really need this to be a string, you can explicitly delete the overload that takes a const char star. You can explicitly delete the overload that takes a double if you've got problematic conversions between doubles and floats. We can make our APIs harder to use wrong using delete. Some way to not even have to think about our heap allocated memory other than the containers previously mentioned. Smart pointers, make unique, unique pointers. Number 24, standard unique, make unique. Automatic, safe, very difficult to use incorrectly. Interestingly, unique pointer relies on equals deleted member functions, destructors, R-value references. All of these things keep getting built up. Plays nicely with guaranteed copy move elision for factory functions. I couldn't find the credit for this. Anyone know? Boost could not have unique pointer. That was impossible because they did not have R-value references. It was impossible to implement correctly. So as far as I can tell, maybe Howard Hinnett, the author of R-value references, was related to this. Yeah, Boost had shared pointer. I'm not talking about shared pointer. Shared pointer, unique pointer is like this awesome thing that does exactly what we want it to do. Or unique pointer is, sorry. Shared pointer is one of the biggest hammers in the C++ tool shed. I want to make a quick summation function. How do I sum these values in this variadic template function that I've written? What was that? Fold expressions. It is possible to do this recursively, by the way. This is code that many of us wrote in C++ 11 days. I know I have. I can do this recursive thing. It counts down until it gets to the 1th parameter. The 0th parameter returns it and adds them up. Can be horribly slow at compile time, difficult to optimize, difficult to debug. Who has written this little trick? That's a fun one, right? Totally maintainable and obvious code. Clearly, we are using the list initialization of an initializer list to sum up these values with this variadic expansion. And obviously, the comma operator, of course you need the comma operator here because you don't know what those types are, so you actually need to return 0. So we're actually generating an initializer list of integers that's packed with nothing but zeros, but result happens to contain the thing that we want when it's done. Right? All right. This one, yeah. This common type T, use that. Fold expressions were already mentioned. Some handy way for us to sum up those parameters for us. This is C++ 17 fold expressions. Definitely less hacky than the previous version. What's that? Don't I need plus 0? I am assuming at least one parameter was passed in. If I did plus 0, then I would be... yeah, I would allow... If I did plus 0, though, I'm making another assumption that it is a numeric type of some sort. And this code could actually work with standard string. Plus T braces default initialize. Well, no, I can't do plus T braces because I don't know which T. I would have to add a first one. That's the... Your point is valid, but yes, this code does assume at least one parameter was passed to it. Although if you call some function with 0 parameters, what are you expecting back anyhow?
This code has less compile time over the first code you showed us. You know, the first example
So this one? This, yes, so this is horribly slow at compile time, potentially. This, relatively speaking, is free. Because the compiler knows exactly what we're intending here from a compile time perspective. And this gets expanded out to be all of the summations all happening at once, and it returns the thing. There's no recursive functions that it has to deal with. It doesn't have to try to optimize those away or anything. It becomes a single expression of a bunch of additions. Yeah. Okay. Bold expressions. Variadic expressions can be used with any common operator. It's a bit of an understatement. I say any common operator. It can actually be used with uncommon operators that make no sense, like the arrow operator. But it can be used in many ways. C++ 17, Andrew Sutton, Richard Smith. Sorry. So that's my 25 points here. We have a C++ standard. We have const, deterministic object lifetime and destruction, templates, algorithms, the standard template library. Standard array, list initialization, variadic templates, const expr auto, lambdas, range-based for loops, R-value references, defaulted and deleted functions, unique pointer. C++ 14 fixed many of the little issues with C++ 11, relaxed const expr, generic and variadic lambdas, return type deduction for normal functions, and make unique. C++ 17, structured bindings, string view, class template argument deduction, guaranteed copy elision, fold expressions. C++ 20, concepts, hopefully text formatting, ranges, and, contracts. Sorry, we ran out of time to talk about contracts. It worked out. We do remember this code, yes? What is the return value? It is 3. 3.0 in this particular code. That is approximately 3.0, I guess, right? Because it's floating point math after all. Is 3.0 perfectly representable in IEEE? Yes, it is. Yeah. How do we catch something like this? Static assert. Okay. Yeah, maybe. Curly braces initialization, that's true. I could use that here. Anything else? 22.0, yes. No, but I want to catch, okay. I know that you would have definitely gotten that code right, but you don't necessarily trust your coworkers to get it right, right? Tools. Tools. Compiler warnings. We are at the heyday of C++ tools that are available. Some of you, I can tell by looking around the room, are younger. You don't remember the prehistory when we had terrible compiler warnings and even worse compiler errors, and we didn't know what our code was doing most of the time. Today, we've got sanitizers, we've got compilers, we've got static analyzers, testing frameworks, fuzzing. Clang tidy with modernize. A lot of the things that I showed you from C++ 98 code, you can run Clang tidy's modernizer, and it'll just update it to be better code. CPP check, which is a free static analyzer, has the ability in some cases to say, that thing you're doing right there, that's an algorithm. You should be using an algorithm right there instead. We've got fuzz testing is absolutely amazing. I've successfully used fuzz testing to find all manner of bugs in my code. The sanitizers, who's familiar with the sanitizers? Okay. Who uses Clang and is not familiar with the sanitizer? You have homework to do. The sanitizers are amazing, and actually there's versions of them for GCC as well, not just Clang. So what I see when I look at C++, and I will say when I started preparing this talk, it wasn't as clear to me as it is today when I got done with it. Our common idioms in C++ actually get easier to express. Language semantics get more consistent. We can do things like variadic parameter packs in more places, auto in more places. Memory management issues almost go away. I honestly cannot recall the last time that I had to deal with a memory management bug in my code. And it might have been a circular dependency or something, like things not being freed. In general, we think less about the lifetime of our objects if we just trust the compiler, use the tools correctly. It's easier to construct. What's that? Oh, I thought I heard someone say something. It's easier to construct libraries that are hard to use wrong. Do not underestimate this. This is key to writing good modern C++. We haven't hit on the power of contracts or properly constraining function arguments with concepts yet. Contracts, if you're not familiar with those, go look those up also. That can be the rest of your homework. They help us make pre- and post-condition guarantees about our code, definitely coming in some form in C++ 20. These are the people who have been involved at the least, plus many, many, many more people. Is uncountably many people provide feedback on these things, and there's lots of people that go to the standards meetings. These are simply the names who ended up on the papers that went to these features. So again, this is who I am, and if you want to contact me, that's my website. I will be teaching at NDC TechTown coming up in September, and again at CVPCon when an applied const expert class. So thank you everyone for coming. I've got stickers here, but are there any questions? I think we have like 4 minutes. Fold expressions, yes. What does the compiler generate? So there's left fold, right fold, inner fold, outer fold, left inner. There's the 4 different types of folds, and it depends on where you put the ... relative to the operator. Yeah, for the example I provided, it literally is going to generate the first parameter plus the second parameter, parens, plus the third parameter, paren, plus the fourth parameter, paren. It generates that exact expression. And you can switch which side the ... .'s on depending on which direction you want it to do the fold. Yes. Yeah, well, although it's sometimes hard to remember which way it goes on the left or the right, and but yes. If you go to CVP reference, it shows specific examples of all of it. Yes?
30 seconds on spaceships, please.
30 seconds on what?
Spaceships.
Spaceships. I didn't mention the spaceship operator at all. Spaceship operator will give us a tool in C++ 20 to automatically generate comparison overloads for our user-defined types. So we will be able to do something like operator less than equals default. It gives us a whole new set of things that we can explicitly default. Or operator spaceship equals default, and it'll generate all the things for us. I think it looks great. I am totally looking forward to being able to use it. The specific implementation details of it and what it means in some situations, I know some questions have come up about, because the spaceship operator itself does this kind of -1, 0, +1 comparison result, and that might not be the most efficient thing for every situation. I haven't looked into those details myself, but I think they'll probably get resolved by the time we get C++ 20. I'm not too worried about it, but I think it's a good one, yes. Anything else? Yes?
You asked about the annoying features. There is one that stays from 98, which is the possibility of activating a non-const member function on temporal.
a non-const member function on temporaries, or the possibility, okay. So if you return an object from a function and then call a non-const member on it, that is allowed from C++ 98, and it's still allowed in C++ 20. And that's true, although I've never personally had that bite me. I've never had an issue with that code. I know some people used to recommend returning a const value from your function. Absolutely, yeah. As of C++ 11, never do that. Never return a const value from a function because it can break other move optimizations. So yeah, I agree that it's a weird one. It's never affected me personally, but.
Let me give you an example.
Okay.
You can overload operator plus plus as a member function, and you will be able to increment, post-increment even a temporary, while if you implement it as a non-member function, gets a non-const parameter, then it will work correctly.
So a post increment of a return temporary and overload. Yeah, that's interesting. Yeah. Sorry, I think I have time for one more one. What's that? Oh. Yes. Make the member an L value reference specifier and it would prevent the issue. Right. I knew that. One more question at most. All right, thank you, everyone.